So yeah, I think we'll move now on to our final speaker, Tim Lam, who is also one of our Fresh Eye subgroup co-chairs. He's the lead of the data request subgroup. He's also recently started a postdoc at Potsdam Institute for Climate Impact Research, looking into estimating future fire risk and its atmospheric drivers. And today he's going to present on causal teleconnections to drought and fire risks in Indonesian Borneo in the past and future. Thanks, Tim.
Hello, and I hope I'm audible. And thanks, Bert, for your introduction. That really saves me a few seconds. And I'm really glad to be invited to give this talk. And it's really great to have a variety of speakers from different backgrounds. So we're moving from mitigation and model development to how we're going to make good use of the available big data of CMIP 6 to inform decision-making against climate hazards. So we're moving towards like impacts and adaptation. So I'm going to present my PhD work, having recently completed at the University of Exeter and the Met Office, which is about looking at the drought and fires in Indonesian Borneo. So I would like to take this opportunity to thank my supervisory team. So first thing, why Borneo? So it's of course a lot to do with the high impact fires in the region happening over the peatlands. So these peatland fires have been posing a lot of negative effects to the natural environment and also the livelihoods. And it's also a primary cause of the transboundary air pollutions across Southeast Asia. And not only that, but also, peatlands is a huge, it acts as a big major carbon sink. So the fires which eliminate these peatlands will mean that it will create a huge setback for our net zero emission targets. And that's why these fires really need to be avoided or at least be reduced at all costs. So of course, there are many human factors involved, but it's very well known that these peatlands, when they are dry enough and they become flammable and they will burn very easily and fires could easily spread. So it's a lot to do with the droughts happening in the region. So one of the approach that we are looking at to mitigate these fires would be to enhance the early warning by looking at some of the large-scale ocean atmosphere drivers of these fires. So we're also interested in looking at how both the drought and fires and also the large-scale climate drivers might change under warming climate, and that will help us to develop a climate risk assessment and resilience building strategies against these fires, which I'm working with a consortium of Indonesian and UK universities on a Kali project, where you may learn a bit more about these fires and also different aspects of these. So a little bit more about the study area. So it's located in Indonesian Borneo, and a lot of fire hotspots are happening over the peatlands over the central Kalimantan province. So the region consists of a distinct wet and dry season. So as it's located in equatorial Asia, you might expect that, and indeed the temperature stays pretty much the same. So we wouldn't call it summer or winter there, but the dry season happens over the northern hemisphere summer. So in June, July, August, JJ8, which is the season that I'm going to focus on. And it's worth noting that these fires only happen during the dry season, and because the peatlands have to be dry enough to burn. So if they are dry, they will easily burn, and if they are wet, then they won't burn. And in some cases, even during dry season, they still get a lot of rainfall. But in other cases, when there's a drought and the rainfall gets below a certain threshold, or perhaps there's a long period of dry weather, and the fires could easily set up. So this allows us to simplify the scientific question to look at droughts, and we could easily use the observed and also the climate model data to approach this issue. So when I talk about the drivers of droughts I'm talking about the remote teleconnections, which are the source of predictability from physically separated regions. So, well, the approach to look at that is to use some we call it the causal inference and causal network. And Cashman has published a paper on BAMS a few years ago, which adopt this approach called knowledge-guided causal inference, which I'm adopting for my study. And so the first thing to do is to set up a causal hypothesis based on our physical knowledge. So it's very well known that these fires are related to the El Nino. So we say that the El Nino southern oscillation is a strong driver of the Borneo rainfall, and they tend to occur like concurrently. So they both occur during the summer, the northern hemisphere summer. But I want to source some sources predictability. So we also want to look at some of the precursors of ENSO, and what prominent ones would be the North Pacific Meridional Mode. And it drives the sea surface temperature over the Northeast Pacific, so it elevates the sea surface temperature, and it turns to weaken or reverse the trade winds over the Western Pacific, Equatorial Pacific, and in turn leads to enormous subsidence over the region. So, that's the causal hypothesis that I set up. And the second thing to do is to collect the relevant time series. So we could easily do that with the observational data, for example, the precipitation, the SST, and other wind data. And it's easily downloadable from various sources. And using these data, we're able to estimate the causal effects. So how we do that is to use some simple and multiple correlate regressions. So you might argue that, oh, of course, a correlation doesn't imply causation. But here, the BAMS paper, the authors in BAMS paper argued that since we have the causal hypothesis in place, and this is built based on our physical knowledge, these figures indeed would reflect the causation behind the physical and it proves our causal hypothesis. That if we are seeing some statistically significant correlations, so these are the beta coefficients based on standardized and detrended data. So we have a set of correlation coefficients. For example, we are seeing a very strong correlation between the ENSO and the rainfall. So it's negative correlation, which means that the positive ENSO, which means El Nino, would act to reduce the rainfall in the region. And also the sea surface temperature over the northeastern Pacific will also act to reduce the rainfall in the region. And it's also worth noting that this minus 0.26 is approximately a multiply, the multiple of these two coefficients. And this is indeed shows the path tracing rule of teleconnections, which means that indeed the causal the mechanism indeed follow this kind of causal pathway. So not only we can look at rainfall, but also using a drought indicator, and this time the correlation coefficient would flip around, but we're also seeing some very significant correlations. And this is based on maximum number of consecutive dry days. So apart from the simple and multiple linear correlations, I've also used some causal discovery tools and also prove that these are indeed the causal links, but this is not the main focus of this talk. So I've done with the starter, which is about the causal teleconnect, how I set up the causal network. So I'm going into the main of this talk. Yeah, bear in mind that this is a CMIP seminar, so I'm going to introduce the number of the CMIP models that I've been using. So we analyzed the outputs of a suite of coupled models from historical simulations and the scenario MIP project to unfold the future changes of the droughts and fires and their drivers under warming climate. So comparing historical simulations against the observational estimate serves to evaluate the representation of drought and these causal drivers in the model, and comparing the historical and future simulations gives the overall change in the drought and its causal drivers and range of different outcomes representing the uncertainty. So yeah, I'm not going to crawl into how this is done, but we'll rather show you a box plot which visualizes the results. So this is a multi-model ensemble. It's good to bear in mind. So this is showing the Borneo rainfall captured by, simulated by the models that have been used. So these are the box and whiskers plots. So what do they mean? So you can see the interquartile range, sorry, the quartiles at the boxes, and also at the ensemble mean with the black line. And also we are trying to, as I said, comparing the historical with the observations in order to sort of evaluate the models. And I'm using different baseline period. Yes, so I'm using a baseline period as the historical period to compare the observations. So and also I'm using a near and far future simulations from SSP2 and SSP5 scenarios to look at the effect of different warming levels on the rainfall, droughts, and also the drivers of these. So you can see, unfortunately, the models are a little bit all over the place, but fortunately, the ensemble means still fall close to the observations. But it's good to notice that some models are too dry, some of them are too wet, and there's no clear signal towards the future. It stays pretty much more or less the same on the ensemble mean, but it's also worth noting that the drier models are getting a bit drier, the wetter models are getting a bit wetter. So I think that's quite a thing. Tropical rainfall, we're seeing different regions. There have been a lot of discrepancies among the models. So this is just one of the examples in Indonesian Borneo. So the second thing we look at is the driver. As you could recall, we have a strong correlation, negative correlation between the ENSO and the Borneo rainfall, showing the observations. So the first thing that we see is we want to see whether models can also reflect this correlation and the causation which are reflected. So you can see some of the models, they do okay, but the others, they don't. So it overall leads to the under-simulated ensemble mean, but it's not by much. So we observe, we see a significant correlation, and with this, with a lesser coefficient, but still strongly statistically significant. But the problem is that we are seeing quite a few outliers which do not seem to capture this correlation very well. And it's worth noting that those models are also the ones which tend to simulate, over-simulate the rainfall. So perhaps the dry or the normal models, they tend to capture this correlation better than the wet models. And there's a very slight strengthening of this association between the ENSO and the Borneo rainfall towards the future, but it's not supported by statistical significance or intermodal consensus. So another driver, as I mentioned, which occurs it drives the Borneo rainfall at the seasonal timescale from March, April, May towards the Borneo rainfall in June, July, August. Is going to show a strengthening trend towards the future. As you could see, it's quite significant even under the SSP2 scenario. So indeed, this is supported by statistical significance and also intermodal consensus. And I forgot to mention that models overall, they capture this this association pretty well. So apart from the rainfall, I think it's also important to look at drought indicators. And for my case, I'm using the maximum number of consecutive dry days, as I showed you initially. With the observation, compared to observations, you can see it's also all over the place, and also, but the ensemble means quite close to observation. So of course, the wetter models, you would expect them to have a lower number of dry days, and drier models with higher number of dry days. So under the SSP5 scenario, you could see quite a significant uptake, like under a very strongly warm climate. And you could see the majority of the models, and this is indeed supported by statistical significance as well. And it will be increasing by 56% on average compared to the historical baseline. And this is also supported by intermodal consensus. So a take-home message here is that it's good to look at the drought indicators, as it may give a different outcome with just looking at the rainfall, as we might be able to anticipate that the rainfall might become more concentrated as downpours in summer time, while the dry spells are also getting longer, and this will have a huge implication towards the fires. So the next thing that we're trying to see is the ENSO versus maximum number of consecutive dry days. So you see that the coefficients are flipped around. As I said, that's because lower rainfall means more dry days. So you can see I'm drawing a similar conclusion with that for the ENSO versus Borneo rainfall. But there's one more thing to add, which is that the members that project a strong increase in maximum number of consecutive dry days also tend to produce a strengthening association. So this is quite interesting in the sense that while it is pretty uncertain whether the maximum number of consecutive dry days might increase or not, but with the increasing number of dry days, we're also seeing a strengthening association with the El Nino, which implies improved predictability. And this is indeed also shown using association using the SST over the Pacific at the seasonal timescale, and we're also seeing a strengthening association under both the SSP2 and the SSP5 scenarios. So to conclude, using these observations and the CMIP models, we're able to depict the teleconnections driving the Borneo drought. And although the things are largely uncertain, as you could see, we are still able to see some signals, identify some sources of predictability that might be strengthening. So that comes to the take-home message of this work, which is that as droughts or fires worsen, they may also become more predictable. And I hope that we send a strong message to the stakeholders in Indonesia that they might be able to, while they might be able to anticipate worse fires, it also might also mean that they could harness this strengthening of the relationship to actually develop a better predictive system against it, so that people could be more well prepared. For example, stop some of the human activities which trigger the fires, so fires won't be triggered in the first place before they actually get spread during droughts. So thank you much for listening, and look forward to your feedback and questions. And I almost forgot to mention that this work was recently published, and if you're interested, I'd be very happy if you could take a look at the paper as well. So thank you very much, and look forward to feedback and questions.
Thanks, Tim. That was really, really interesting work. Has anyone got any questions for Tim? Please feel free to put your hand up, or alternatively put it in the chat again.
I just ask a quick question, Tim? So I was just wondering, like, building on your results there, looking forward to kind of the next generation of models, how would you perhaps expect like increasing resolution, or perhaps, you know, more complex models with interactive vegetation to impact the results?
Sorry, Eleanor, are you referring to the regional model, like some of the features of regional models that?
Yeah.
Okay. Just sorry, continue, please.
Yeah, just like how those kind of developments could potentially impact and perhaps sort of change, or you anticipate could affect your results.
Yeah, definitely. That's something really interesting. So for my results, I'm mainly looking at the SSP2 and this SSP5. So the regional, more like the fire danger elements other than the rainfall and droughts are kind of prescribed. But in the project I'm involved, in the consortium that I'm involved, there are also some recent studies being published, and they exactly use the kind of regional models that use. So they find that indeed a deforestation will definitely have an impact, and will definitely lead to increase of fires, and that's of a very high confidence because of the evapotranspiration, the increase in evapotranspiration and the wind speed due to the removal of the forest. So it's not to do with the land use change and deforestation side of things as well. And there are also some recent studies which show that the deforestation may also act to reduce the rainfall and that is probably not reflected in the runs that I've been using. So yeah, I think probably that would mean further increased drying compared to what I've shown, and that some quite a strong signal as well. And if you're interested, of course, I'll send you the relevant papers.
That'd be great.
Yeah,
Thanks very much. That was a great talk. Thank you.
Yeah, thank you so much, Tim. And thanks again to all of our speakers today. It was a really interesting, varied set of topics that we heard about. So this was our first of our new monthly seminar series. We're always looking for speakers. You can kind of sign up at this link if you have any work that you think would be interesting to share. We'd love to hear about it. We've also moved so every other month it's at a different time to kind of allow for participation from people from all different time zones. We've changed the time zone for next month to 8 a.m. UTC, just to flag to everyone. So yeah, please sign up. We'll look forward to hearing another set of really interesting talks in a month's time. And we will also be uploading most of the talks to YouTube, so you can always catch up on any talks you miss if you can't make a seminar one week. Thank you so much all for coming, and we look forward to seeing you again next time.